Hey, class, I thought I better tackle this problem. Nobody's got there quite yet, or at least has asked me. And looking at these problems a little carefully, realized that there's something that was covered in this harder textbook, the university physics one, that wasn't covered in yours. So I'll begin by saying, look, if you don't want to do this problem, you don't need to. Fair enough. You can skip it, and you don't even have to watch the rest of this video, and let's call it good from there. But if you're a little more curious to what's going on here and this problem, let me point out that besides having this idea that velocity is wavelength times frequency, there is a nice equation that says if you have a string and you make a wave on it and it travels down, its velocity depends on, and there's two factors here. One is how much tension is the string under, and the other then is how much mass per length are you then moving. And it kind of makes sense that there would be this, I'll call it the restoring force. When you make a little hump here in the wave, the more the tension, the more it kind of snaps back, making it travel faster. And also then, the lower the mass per length, in other words, how much the string actually weighs. And not the whole length of the string, but just the string per length, because you're just making a little hump. You're not making the whole mass move. You would think that the smaller that is, the faster it would make it move. And that's true. Now, the derivation takes a little bit of effort, either a little bit of calculus or a little bit of circular motion. So the square root's not so obvious. We like to write it this way. The velocity equals the square root of tension over mu, mu being what we call the mass density, or the mass per length, and T being the tension, although that can be confusing because we also use a capital T for period. And so I just wanted to spell it out the first time, and maybe I'll even put a TEN from here on out to say, look, that's the tension in it, not the period in it. And like I said, here's why you can kind of skip this problem. I just went back and looked at your book, and your book doesn't derive this. And as I mentioned before, it's not the normal set of class I teach, so every once in a while I find something interesting and new that catches me off guard in this class, as it focuses more on the life science and not on the engineering. Anyways, this is an important piece of physics. I think it's an important piece certainly of engineering. It extends down into sound waves and bulk modulus and the structure of buildings, so I was a little surprised it wasn't in the book, but maybe it's not that important for the life science, and maybe that's why the author has chosen to leave it out, or maybe I missed it altogether. But either way, I'm going to say, same thing, that if you're struggling with this one, just skip it. It's fine. It involves this piece that apparently the author of this book, and maybe I'll learn too, it just maybe doesn't have a good applications into the life sciences. So it's not covered. However, because we are the harder class, the Physics 110 and not the Physics 105, and we're doing some calculus, we throw in a little bit of calculus and a little bit of harder problems from the advanced book, and this would be one of those. So I'll go ahead and work it out, but you need to know that information. Let me not derive it, but at least give you that information to get started here, because here's what it says. It says, consider what is shown below, that we have a 20-gram mass that rests on a frictionless ramp indicated at a 45 degrees. So they have this picture. Maybe I should have printed it. But there is this 20-kilogram mass hanging or supported on a 45-degree incline. Okay. It says there's a string coming up here. And so here's the string, and then they show a little wave on the string. And they say the string has a linear mass density, so mu, of 0.025 kilograms per meter. It's attached to this 20-kilogram mass. The string passes over a pulley and is attached to another mass. Okay, so in this picture, there's like a little pulley right here. The string goes over. I guess we got to support the pulley somehow. All right, so we'll support the pulley. The string comes over, and it has mass m. Okay, and little m. The system is in static equilibrium. A wave is introduced in the string and travels up the ramp. And then the two questions. A, what is the mass of the hanging mass m? And then B, at what wave speed does this wave travel up the ramp? All right, so B is kind of the heart of the problem, and it's getting right to here. If you know the tension in the string and the mass density, you can get the velocity. And that's what we're going to do in B. And of course, to get that tension, we have to realize that this is in equilibrium. And so, if you did a free body diagram of this hanging mass, you've got mg pulling it down and the tension pulling it up. And it says it's just hanging there in static equilibrium. So you know in this diagram, the sum of the forces in the y direction have to be 0 because they always equal mass times acceleration. And in static equilibrium, the acceleration is 0. And so this just says the tension is equal to little mg. Now that by itself I can't do much with, but if we come over to this picture, which we've done a few times, granted it was a while ago, but if we do the free body diagram here, and we've got its weight pulling down, mg, the normal perpendicular to it, the string is tied to it, so this is the tension. And they said it's frictionless, so there's no friction. And if you remember doing problems like this, it made sense to twist our axis, and so that the x-axis is along the incline, because if we do the sum of the forces in the x direction, that has to be 0, again, because it always has to equal mass times acceleration in the x direction. And again, we're just stationary there, so the acceleration is 0. And what's nice about the x direction is all the tension is up the hill, so there'd be a t without any kind of sine or cosine with it. And the other nice thing here is that the normal force is all in the y direction, so I don't need to include it in this equation. And then this is that gravitational force where we said there would be a component down the hill and another component into the hill. And the component then down the hill is the sine of the weight hanging. So I'm going to write that as mg sine of 45 degrees equals 0. Now, I suppose I should be careful with my m because this is the m of the 20 kilograms. So let me put a capital M here because I don't want you to confuse it with this m that I said earlier. But in either case, this gives us a chance to figure out what the tension is. And then once we know that, we can put it up to here to find out, A, how much mass do we have? Okay, so grabbing my calculator here, I'm going to take the 20 and multiply it by 9.8, and I think the last problems we were doing, we were in radians. Yes, we were. So let me switch here to degrees before I go sine of 45 degrees. Okay, and so I get 139 newtons of tension. Okay, So then if I take that and I bring it up to my first free body diagram and divide by 9.8, we need about 14.1 kilograms. And so kind of makes sense, and even without the waves, this part A is kind of a review from way back in chapters 4, 5, and 6. We're dealing with Newton's laws of motion. We just say these have to balance. And so this side has 14.1. Notice it's a lower amount of kilograms because this is on an incline. And it's 45 degrees, so the short answer would be 0.707 times 20, yeah, and we get 14.4. So we know how much mass has to be there to balance it. And so I'll say it again, A really is kind of a throwback to past chapters. That's another reason why I was thinking, well, maybe it's not too important to do this one. This stuff, in theory, you should already know, but in practice, you maybe have kind of gotten a little rusty on it. But it doesn't really help you for this chapter. And then B is the one that I really picked this problem for, thinking it would tie in with the tension. It would be a nice review with the tension. But like I said at the start of this video, I was a little taken aback that your author has not derived this or talk about waves on a string. It's got some really neat applications, and not just for waves on a string, but getting into sound waves and bulk modulus. But again, maybe that's all more engineering, and your author decided didn't need it. All right, so I'll finish up this problem by getting to the heart of it by saying then the speed of these waves, as they asked for, would be the tension on here, which we just said was 139 newtons. And then the mass density was just straight up given, 0.025 kilograms per meter. And maybe I'll separate those into both numbers, and so I'll put the numbers in there, and units. And so taking the Newton as a kilogram meter per second squared, and then dividing it by a kilogram per meter, so we'll flip and multiply, the kilograms would cancel off. And in the top, you would have meters squared, which when you take the square root is a meter. And in the bottom, you have seconds squared, which when you take the square root is seconds. And so, again, our unit analysis works well. We get the appropriate units. And like we said, if we didn't get that, we would be concerned that our formula wasn't right. Something went wrong in our logic, because our units need to match what we're supposed to be measuring. And velocity is measured in meters per second, and the units do match. So that's perfect. All right, so taking this 139 and dividing it by 0.025, and then taking the square root of all of that, I would get a speed of about 74, I'll call it 0.6 meters per second. So, like I said, that was kind of the heart of the problem, kind of what they were after. And for you guys, you can kind of skip over it, since I guess your author doesn't use it. We won't be needing it then, I would assume, later on next semester. All right. Take care.